set up a Riemann sum for 4 minus x squared here from 0 to 2. So my delta x, 2 minus 0 is 2 over 10, which we could reduce down to a decimal or a fraction. I'm going to leave it as just an unreduced decimal or fraction right now.
So you chose your n, you said, okay.
Yeah, I'm going to start with n equals 10, and then I'm going to let n be n after. But sometimes, like if I'm just asked to do n in general, sometimes I need to throw a number in there first to just get it set up. So then I want to do my xi's, and then I think in general, right is the way to start unless you're asked to do something else. Right endpoints are easier. They're always a plus delta x times I. So for this one right here, that's going to be 0 plus, I'm going to leave it as 2/10 I, which is just 2/10 I. All right, starting at 0 is nice. It means your xi's are easier. Otherwise, you have to add something to that. And then the function value for that, so f of xi is going to be 4 minus parentheses squared. And I'm just going to leave it as 2i over 10 for now. But usually I'd reduce it to like 1/5 or 0.2. So all I'm doing is replacing x with the x value I calculated there. And so then the Riemann sum for a right endpoint, so R10 in this case, will just be the sum as I goes from 1 to 10 of delta x, 2/10. And again, that's always going to be a multiple. You could always put that out front for the problems that we do, because it can be factored out, times 4 minus, having trouble reading 2's there, 2i over 10 squared. And for more than 3 or 4 or 5 pieces, I do it by hand because I can just kind of look at the graph and get it. For this many, I'm just going to go to my calculator and plug that in. So whip out your favorite calculator, Desmos, GeoGebra, and try to type that in right there. And again, the sum is always your delta x times your function values for the xi's. Let's see. I want, sure, I can do sum. Okay. Expression is 2/10 times 4 minus 2/10 I squared. So Desmos is a little clunkier. Now GeoGebra is a little clunkier for typing in sums. Do I have that right? No. My variable is I, starting at 1, and going to 10. I'm getting 4.92. If I typed it right. Anyone else get that? Yeah. And again, some things GeoGebra does better, some Desmos does better. Desmos. And again, if you typed this ahead of time, you can actually reuse it. So if I have my 4 minus x squared here, and I guess I could have done that in GeoGebra. I didn't cross my mind at the time, but the sums are prettier here, right? 1 to 10. So I could either type it as 2/10 times parentheses 4 minus, they want to use n here, so it'd be 2n over 10, and then squared. And I should get the same answer. But again, because I have the function above, an easier way to do it, I don't know if you guys remember this, sum from 1 to 10 of delta x 2/10 times, and I can just type f of 2n over 10. So benefits of using function notation. GeoGebra would handle the same thing. All right. Does that seem like a reasonable area? Oh, both Desmos and GeoGebra can do numerical integration for us. We could check that here too. Okay. We're using a right-hand endpoint on a decreasing function. Is that an upper sum or a lower sum?
Oh,
Yeah, draw a picture, right? If I look at the picture, right-hand endpoints here are going to be a lower sum. Yeah, so it's going to be an underestimate of what the actual one is. So does 4.92 seem like a reasonable underestimate with 10 rectangles for 5.333? Probably. So what's the point? Do I think I set up my Riemann sum correctly? I think so. Okay, so from here, again, if you didn't reduce, then the general Riemann sum is actually not that hard. We're just going to replace the tens with n's and see what happens. So I'm going to get Rn is the sum as I goes from 1 to n of 2 over n instead of a 10. So again, my goal is just to replace the tens with n's times the function 4 minus parentheses 2I over n squared. So that should be the general Riemann sum for this, right? Not too bad if we don't reduce. Next question, can we clean this up? So to clean it up, I'm going to pull out the 2 over n and then split the sum over the difference and see what happens. I'm just going to restart that on the next page. So Rn so I'm going to get 2 over n times the sum of a bunch of 4s. So I pulled the 2 over n out and distributed the sum into the interval, into the sum, minus, I'm going to also carry the 2 over n with the sum, I equals 1 to n. Now here, I remember I is the only real variable in there at the moment. So I'm going to carry out that square and call that 4I squared over n squared. Because then I can pull out the 4 and I can pull out the n squared in the bottom. Okay, before we do that, what happens if we add up a bunch of 4s n times?
4.
It's 4 times n. Yeah, so that right there is 4 times n. Right? If it was 10 4s, it would be 10 times 4. 100 4s would be 4 times 100. So this here is 2 over n times 4n, and that cleans up kind of nice.
Yeah.
That part is just 8. Well,
Can you explain that more times?
what's that?
The 4n part?
Yeah, why that's 4n? Yeah, so that sum basically says take 4 and keep adding it to itself however many times, and we happen to be doing that n times, right? So if n was 10, it'd be 10 times 4 is 40. In this case, it's just 4 times n, whatever that happens to be. Then we get some nice cancellation with our delta x. The other part, 2 over n is a multiple on the outside, but I can pull that multiple of a 4 out, and I can pull the multiple of n squared out. So now I only have to worry about summing the I squareds. And the sum of the I squareds isn't something I expect you to memorize. I'll just tell you it. So it is, so just that right there is n times n plus 1 times 2n plus 1 over 6. multiply that by what we have over here, which is 8 over n cubed. So now for any number n, like if we plug in n equals 10 there, that should give us the same answer we got before. For that 4.92, right? For the sum we did in GeoGebra. Okay. So again, sum of the I squareds, I will give you that formula on the test. All right, so what do we have here? Well, at this point, we're ready to take the limit as n goes to infinity. And of each of these things. So I'm not going to recopy them. As n goes to infinity, what's happening with 8? It's just 8. Yeah, so we're going to get an 8. And then the other part is an n times n times n. It's a cube divided by another cube. Now be careful here, though. This is n times 2n. So the leading coefficient in the top would be related to 8 times 8 is 16n cubed, blah, 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 divided by 6n cubed. So that one is going to be a minus 16 over 6 in the limit, because those are the leading coefficients. And again, I don't have to multiply all this out. I just need to know what's attached to the n cubed. 16 over 6 reduces to what? That's going to be 8/3. So 8 minus 8/3. That would be 3 times 8 is 24 minus 8 over 3. And again, a calculator would be a good thing here. 24 minus 8 is 16. No.
16 over 3.
Yeah, 16/3. Is 5.333 repeating, which is what the computer told us before. Holy shit, that was hard. Alternative. Fundamental theorem of calculus. Antiderivative. Integral from 0 to 2 of 4 minus x squared. Antiderivative for 4. 4x. Antiderivative for x squared. 3. Reminder, that's from 0 to 2. Plugging in, 4 times 2 minus 2 cubed over 3. That looks familiar. Minus, and it's always good to double check, because plugging in 0 doesn't always lead to 0 for all functions. But 4 times 0 minus 0 is 0 minus 0. So this time it works out. But write that down just to double check to yourself. Just don't assume that's going to be a 0 out there. So there's my 8 minus 8/3, which we already calculated as 5 1/3. Last big thing we need to review really is substitution, I think was the next hardest thing we did, or maybe total area versus net area.
Oh, yeah.
So let's look at a couple of those.
Antiderivative is just the net area.